Hello, everybody. This is Mr. Fasoni. This is the first of the videos for semester 2. Like I mentioned in class, the videos are going to be shorter. It's going to be more about just doing examples versus the lecture, which is now going to be entirely in class. I still have the same slide deck up, so I will talk about things briefly, but I'm going to be doing more problem solving as examples for your reference as you're working through the homework. So once again, this is chapter 6, exponential and logarithmic functions. And chapter 6.1 is specifically about exponential growth and decay functions. So we had the goals, we talked about those in class. Just a reminder, exponential functions are always in the form, or at least the standard form of them is y equals a times b to the x. A cannot equal 0. If it did, everything on the right side of the equation would equal 0, and we would just have y equals 0. And the base value, b, is always a positive real number other than the number 1. And then if b is greater than 1, we have exponential growth. If b is between 0 and 1, we have exponential decay. And then the simplest type of function is when a is equal to 1, we just have y equals b to the x. We get rid of the a value because anything times 1 is just itself. No need to write that extra 1 in there. All right, and then we have the parent functions. Just remember the parent function is either an uphill growing slope if it's a growth function. As we go from the left to the right, it's rapidly steep slopes uphill, becomes a steep uphill slope. Some points to keep in mind are 0, 1. In other words, when x is equal to 0, if I plug it into the function, I get y equal to 1 out of that. And then when x is equal to 1, if I plug a 1 into the function for x, the value I'll get out is whatever my b value is, because b to the first power is equal to b. And then for the 0, b to the 0 power is always going to be equal to 1. The domain's all real numbers, so any x value can be plugged in. The range will always be positive, so all of our y values are going to be greater than 0. The decay function looks exactly the same, except it's going downhill as we go from left to right. You can basically think of it as a horizontal reflection from left to right from the function above. And again, we talked about this in class. Again, the special points are in there. B to the 1 is still equal to b, and b to the 0 is still equal to 1. Domain and range still work the same way. Okay, so the first goal we talked about in class was the growth and decay functions and understanding what the graphs are going to look like, particularly whether it's going to be growth or decay. So we did the first two in there during the lecture, but I'm going to do these other ones, 9 through 17, very, very quickly. So remember, all these functions are effectively y equals a times b to the x, or f of x equals y a times b to the x, but f of x isn't in there this time. So one thing to quickly realize is that the x value is always attached to the b. And on all of these functions, a is equal to 1, so it's not even showing up. But even if it does show up, it doesn't really matter what a is, as long as it's a positive value. We're going to have that standard growth function that goes up as we go from the left to the right. We'll talk about a as a negative value later on, but really it doesn't have any effect at this point. So really all we have are b values. So if I just look at these, I've got a 6 for b, 1/6, 4/3, 1.2, and 0.6. So this goes very, very fast. I'm just comparing the value to 1. Is it bigger or smaller than 1? 6 is bigger than 1, so the first one's going to be growth. 1/6 is less than 1, so it's going to be decay. 4/3 is greater than 1, so it's going to be growth. 1.2 is greater than 1, so it's going to be growth, not 6, a G. And then 0.6 is between 0 and 1, so that's going to be decay. It's easy as that. You're just inspecting that B value. And then we've got a couple of graphs. These ones are also very easy once you understand what you're looking for. We're trying to use the graph f of x equals b to the x to identify the value of the base b. Well, remember, let me go back. Remember, when x is equal to 1, my y value is going to be exactly b. So I can find that very quickly if I look at these graphs. I've got a point where x is equal to 1 on both of them. So since x is equal to 1 on the first one, b is going to be equal to 3 because 3 to the first power is 3. On the second one, my b value is going to be 5, because when x is equal to 1, my y value is equal to 5. And it's as easy as that. All this other stuff is just extra information. I mean, you can see the relationship. -1 would be to the negative first power. Well, 3 to the negative first power is going to be 1/3. Same with over here. 5 to the negative first power is 1/5. I don't know if I said negative the first time on the. It's not negative 1/3 or negative 1/5. It's positive 1/3 and 1/5. All right, let's continue going forward. So next after that, we talked about exponential models. This is just kind of an expansion and rearrangement of the model. Remember, the model is y equals a times b to the x. Well, when we're talking about real life situations, we can remodel it as y equals a times 1 plus or minus r to the t power. So r is our rate. T is our input, and it's just time. When you think about a graph, as we go from left to right on an informational graph, we're looking at time a lot. You know, if we've got some kind of chart in National Geographic, for instance, and it's talking about the human population of the Earth, it's going to look something like that. And you're going to have time on the bottom. On the vertical axis, you'll have your population. And it kind of looks like that exponential function over time. It kind of grows slowly at first, and then it rapidly goes up. This could be the year 2000, and back here could be the year 1800 or something like that. So you're thinking of time as the input, and then the only difference here with the stuff inside the parentheses is just to remember that this b value is a singular number. It's going to be either greater than 1 or between 0 and 1. Well, that 1 that we're starting with, that represents 100%. And then if we're growing, we're getting larger than 100% of our original value each time period. So it's going to be 100% plus some other percentage in the form of the rate. Or if we're decaying, we're shrinking. So we're starting with 100%, we're subtracting some percent from that. So after each time period, we're shrinking to a value less than 100% of our original amount. So this b value from the original function is just really being replaced by 1 plus or minus r, depending if it's a growth or decay function. And then y and a stay the same. So these are the models. This just goes into more detail. We talked about that in class. We had a real life problem that we did, and I've got some other real life stuff over here that I'm going to do. And I think I've got a couple. So this is a little bit more involved. This is all about kind of reading through and understanding what's being said. So the value of a mountain bike y, that's what we're going to be calculating in dollars, can be approximated by the model y equals 200 times 0.75 to the t power, where t is the number of years since the bike was new. We don't know what year it was purchased or whatever, but that is irrelevant because we're basing it off from when the bike was new. We're counting from there, and we don't have to factor in years or anything like that. So this is y equals 200 times 0.757 to the t power. So just identifying the numbers really quick, 200 is my a value. This is my starting value for the bike. So really, that means we started with a value of $200, right? We're leaving the dollar signs off, but it's a $200 bicycle. And then my 1 minus b, because it's 0.7, not 1 minus b, 1 minus r, because 0.75 is less than 1. So you can think about this, 0.75 is technically a b value, but it's going to be equal to some 1 minus r value. If we think about it like that, we start with 100%, we subtract some value from 100% to get down to 0.75 or 75%. And just recall the relationship between decimal and percent. 1 equals 100%, 0.5 equals 50%. So if you're going from decimal to percent, you multiply by 100. If you're going from percent to decimal, you divide by 100. Or you just move the decimal places 2 to the right or 2 to the left. Okay, so we got 3 things to do. Tell whether the model represents exponential growth or exponential decay. That's no work other than inspection. All I'm looking at is that B value, or that 1 minus R value in this case, because it's less than the number 1. So 0.75, since it's less than 1, it's going to be an exponential decay function. Done with that. Identify the annual percent increase or decrease in the value of the bike. You have to do a little algebra there. All you're doing is taking this value out. We know that 0.75, since it's less than 1, it must represent 1 minus R. So all we're going to do is solve for R. And you can do this just using basic algebra. I'm going to get R by itself. I'm going to do a slightly different route just for fun. I'm going to subtract 1 on both sides of the equation. These ones cancel. 0.75 minus 1 is going to give me negative 0.25. That's going to equal negative R. Well, that means my rate really is going to be 0.25. And if I want to convert that to a percentage, I just multiply by 100, which is going to give me 25%. I'm decaying by 25%. Or in other words, I have 75% of my original value after each year. Or 75% of the value of the previous year, really. So that's going to be a minus 25%, or you can just say 25% decrease. All right, and then estimate the value of when the value of the bike will be $50. This is a little bit more work. You're going to actually, if you're going to do an estimate of when the bike is going to be a certain value, you would actually either have to create a t-chart with your t value for your input, 0, 1, 2, 3, 4, 5, and then your actual value of the bike, which is y equals a times, I shouldn't say a, I should say the actual value of the bike, y equals 200 times 0.75 to the t power. So you can go through this and calculate it pretty quickly. It's a lot of, it would be a lot of busy work, but you can go, okay, well, I know at 0 years, it's going to be y equals 200 times 0.75 to the 0 power, which is equal to 200 times 1, which is equal to 200. We know that. That's the starting value. That makes sense. The next year is going to be y equals 200 times 0.75 to the first power, which is really just 200 times 0.75, which is going to give me 150. What value am I trying to get down to? $50. So I'm shrinking quite a bit. It's going to take some time to get down to $50. But I can continue doing this. I can plug in 2. It would be y equals 200 times 0.75 to the second power. I would actually have to take 0.5 to the second power. That'll give me something like 0.56, something like that. I'm not doing the math with a calculator. I could actually do that really quick. Let me open up my calculator software. 0.75 to the second power, 0.5625. I knew it was a longer decimal. I just couldn't remember what it was. I multiply these together, I'm going to get $112.50. So it's going down in value. It looks like it's going to take a few more years. So just a quick aside, we could go to something like Desmos, and we could go into the graphing calculator, and from there, I could do my equation, y equals 200 times 0.75 to the t power. Oh, you know what? I'm just going to put x for my power. And if I look at this, I can actually see the chart here. If I zoom way out, I can see my 0 point, my starting point right here at 200. At 0 years, I'm at 200. After 1 year, I've gone down to a value of 150, which I can see right there. I can get that to stay in place, 1, 150. So I could just kind of go along my chart here, my graph, and I can find where 50 is. And it looks like at about 4.8, I reach 50 and I go below $50 for the value. So sometime between 4 and 5 years is when this is going to go below $50. So I would have to do all these equations repeatedly to get down to something that's below $50. So our amount of time to find $50 would be, or to be around $50 would be about 5 years. And notice it says estimate. So I was actually calculating it with that T-chart. The graph is what allows me to estimate it. I just found where I found where 50 was, and I see that it looks like I'm almost to 5 years when I cross that 50 threshold. And as it goes along, it becomes worth less and less and less. All right. So that's an example about using that growth or decay. Let's do a different one here. It's going to be slightly different in what they're asking for. In 2006, there were approximately 233 million cell phone subscribers in the United States. During the next 4 years, the number of cell phone subscribers increased by about 6% each year. So we want to write an exponential growth model, and we know it's going to be a growth model because we're talking about increasing by a certain percent. So we're going to write a growth model giving the number of cell phone subscribers Y in millions at T years after 2006. So 2006 is our start value, and we want to estimate the number of cell phone subscribers in 2008. So our function is going to look something like this. Y equals A times 1 plus whatever our R value is to the T power. Well, let's plug in some stuff that we know. 233 million was our start value, so that's going to be A. Our rate of increase is 6%. Well, 6% is just the same as 0.06 if you convert it to a decimal. So my rate is going to be 0.06. I'm going to bring down the rest of the stuff. And I'd be adding 1 plus 0.06. And T and Y are my inputs and outputs. I input T, I calculate, and I get my Y value. Put that plus. That's still not very good. But T is my input, Y is my output. I've got my general equation. That's the first part of part A. The second part of part A is to figure out how many subscribers they're going to be in 2006. Well, if my start year is 2000, I apologize, 2008 is the year I'm trying to figure out. If my start year is 2006 and I'm looking at 2008, then the number of years that have passed is just going to be 2. It took 2 years from 2006 to 2008. So again, I just, do my equation. This time I've got my input. My input is 2. Everything else is the same as before. It's going to be Y equals 233 times 1 plus 0.06 to the T power, which is in this case to the second power. So I can clean this up pretty quickly. It's going to really be Y, and I'm just going to keep it one color. In fact, I'll go yellow. It looks a little bit brighter. So it's going to be Y equals my start value of 233 million people times, I'm going to add 1 and 0.06 together, so 1.06 to the second power. At this point, it's just calculator time. So 1.06 to the second power is going to give me 1.1236. I'm going to multiply that by 233, and it's going to give me 261.7988 for my value. I don't think it asked us. Oh, and again, it's asking us to estimate. I'm calculating this stuff. I apologize. So if I calculate it, I can get a very exact number. I'll round this to the nearest million. So about 262 million subscribers, not millions, million. But if I want to be more general, I can go back into this Desmos and I can build a new equation. Y equals, what was it? 233 million people times 1.06 to the t power. I'm going to use x for my input in Desmos. And what's going on with Desmos? Why is it giving me? Oh, that's right. It's giving me a graph that looks like this. It's still an exponential growth function, but my A value is 233. So my y-intercept is going to be very, very high already. So we're starting at a very high number and it's going to grow very quickly from there. I need to estimate. The first part was asking the estimate of the value in 2008. And then we also want to know when we're going to hit 278 million. Well, 2008, that's just going to be 2 years. So if I go to 2 years, I should zoom in a little bit. Come on. Here's 1 year. Why is this? I'm zoomed way, way out. Technical difficulties, but you can see at 1 year, I'm at 246 million. And then at 2 years, I continue to go up on this graph. At 2 years, I'm at 261.799 million, which I think is what I calculated. They rounded it to nearest thousandth. So yeah, about 262 million. And then if I want to figure out when we hit 278 million, I just look at my Y output now. And I'm trying to find 278 million. There's 278. I scroll up. It looks like right about a little bit after the beginning of year 3. So 3 years in, we're at 278 million. So I've got my answer for that as well. About 3 years. And we're done with that problem. Again, it's very quick if you know what to plug in. And I did too much work by calculating. I should have just thrown it into a graph and looked at it. All right, let's look at a different one. This is kind of a crazy one. We talked about that power rule where we have a power that is a power of a power. And we use that to deal with this fraction here. So we'll talk about that very briefly again. Let's just go through the problem really quick. When a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. The amount Y in grams of carbon-14 in the body of an organism after T years is Y equals A times 0.5 to the T divided by 5,730 power. That's kind of the weird part. A is the initial amount, and that's always been our A value, whatever our amount is in grams. They don't give us an amount. That's just a general equation. T is the number of years. That's our input. And of course, Y is our output. That's what we're solving for. So we want to figure out what percent of the carbon-14 is released each year. This is kind of crazy. We have an equation that looks like this. A times B to the T divided by 5730. So, and actually, let me rewrite this. Let me take some of the vagueness out of it. So it's Y equals A. Our B value is 0.5, and we've got T divided by 5,730. Our goal is to get to something that looks like this. So I want to eventually have, in parentheses, 1 minus R, so I can figure out what my actual rate is. That is how much I'm changing by. And then I also want to have just a T value for my exponent. Right now I've got T divided by 5,730. This is a little bit weird, but what we can do very quickly is we can use the idea of power of a power. So if I've got x to the m to the n, that's just the same as x to the m times n. That's an old rule from Algebra 1. We talked about it in class. If you need help on this, you can either reach out to me or check out something like Khan Academy or even look in your book. So if I'm dealing with t to the 5,730, or I'm sorry, t divided by 5,730, I can split that into two pieces. I can split that into two pieces where one of the pieces is t and the other piece is a fraction. So I'll go ahead and do that. I've got y equals a times 0.5, and then I'm going to split this into two pieces. Here's do the fraction part first. 1 over 5,730 times t. I'm just reversing the power rule. So I'm starting from here and I'm moving backwards towards something like this. I'm going to rewrite again. You should stop using red so much. Y equals a times 0.5. I'm going to put the fraction on the b value. One over 5730. I'm going to put this all in another set of parentheses, and then I have the t power on the outside. I've got t by itself now. My next goal is to figure out how to get this into the form 1 minus r. So what I'm going to do is I'm actually going to process this. I'm going to evaluate it. So I'm going to get out my calculator. And I'm going to very quickly, 0.5. This is a little bit tricky. I'm going to put it in parentheses, 1 divided by 5730. That's my fraction. I'm going to close the parentheses. This first number that comes up is my closed parentheses. I got to hit the equal sign to finish the problem. And when I do that, I get this number that's very close to 100%. I get, and I'm going to round it to, since it's so many nines, I'm going to round it to 5 digits. So this is going to be 0.999. What was the rest of it? 88. Rounding that 5th digit up from 7 to 8. So now I'm going to rewrite the rest of my equation. Y equals a times 0.99988 to the, this has all been processed. The only thing I have on the outside now is the t power. I'm basically almost done. All I have to do now is figure out what my rate is, and I can do that by just doing a quick algebra problem. 1 minus r is going to be equal to 0.999, it's 9, 88. I'm going to subtract that from both sides. It's not lined up, so just be careful with your lining up of things. I'm going to add r to both sides also. I'm going to get some cancels. This cancels with that. 1 minus 0.99988 is going to be 0.00012, I believe. That's going to be equal to my r value. If I want to turn that into a percentage, I'm just going to multiply by 100. It's going to move my decimal over two spaces. So my rate is 0.012%. And it's a decay rate because I'm subtracting r. So from there, I figured out the percent of carbon-14 that's released back into the atmosphere each year. It is 0.012%. That's the answer to my question. All right. These questions are a quick practice again. Rewrite the function in the form of a times 1 plus r to the t, or y equals a times 1 plus r to the t, or y equals a times 1 minus r to the t. So a growth function or a decay function, and then we have to state the rate. So these are both just like the previous problem with numbers that aren't quite as nasty. So if I've got y equals a times 2 to the t divided by 3, I can rewrite that as y equals a to the 2 to the 1/3 to the t power. And then I can evaluate this. 2 to the 1/3 power. So I can go back into my calculator. 2 to the 1/3 power is really just the third root of 2. So some of your calculators might have the third root. If you don't have it, it's not a big deal. You just do 2 to the 1 divided by 3 power. There's my 1 divided by 3. 2 to this equals 1.2599. So I'm going to round that to 1.25 or 1.26. So this becomes 1.26 to the t power. At this point, I'm basically done. All I need to figure out is what I'm adding or subtracting from 1. You can actually see that very easily. I'm adding 0.26 to 1. There's that 0.26 right there, which means it's a 26% growth. The next one is also very fast. It's going to be a decay. So I've got y equals a times 0.5 to the t divided by 12 power. I'm going to rewrite that. Y equals a times 0.5 to the 1/12, not 1/2, 1/12 power to the t. I can then calculate that very easily as well. 0.5 to the parentheses 1 divided by 12, that's my power. There's my 1 divided by 12. 0.5 to the 1/12 is 0.9438, so I'll round that to 0.944. So 0.944 to the t, y equals that. If I want to convert it, and I forgot to actually write the converted version on the previous problem, I'll technically do that because that was what the problem was asking for. Converted version on the first problem would be 1 plus 0.26. I skipped a step there. On this one, I just have to figure out what my t value is going to be. My equation is going to be y equals a times 1 minus some r value to the t power. If I want to find out that r value, I'm just going to subtract 0.944 from 1. That's going to leave me with 0.056. So that's my equation, and 0.056, if I move the decimal point over 2 times, it's actually going to be 5.6% decay. And we're done. So these become very fast once you know what you're doing. They give you all the information. You're just doing a lot of calculator work and keeping track of where everything is. All right, and then our last problem. We talked about compound interest. That was our last thing that we talked about in chapter 6.1. Compound interest, just remember, it takes that equation that we had before, y equals a times 1 plus r to the t, and it kind of manipulates it a little bit more. We get y, or not y, we're using financial terms on this one. It's the amount at the end, capital A, equals my principal, or my start amount, capital P, times 1 plus my rate, divided by the number of times we compound the interest, or process the interest per year, or per time period, and then it's going to be raised to the n times t power. So a lot of things stay the same. Y is functionally the same as A. It's my final value, and that's capital A. Lowercase a is functionally the same as capital P. That's my start value. These ones still represent 100%. The rate is the percentage growth per year. Time is measured in years in this case. And then the only real thing that messes with stuff is that number of compounds per year. We're taking that interest rate, we're slicing it up based on the number of compounds per year that's happening inside the parentheses there. And then we're also applying that compound to the number of years that we are gaining interest. So we get that number kind of back on the outside of the function, or the outside of the parentheses in the exponent. So I'm going to go through this and just very quickly determine what my values are. So you deposit $5,000 into an account that pays 2.25% annual interest. So once a year, or not, sorry, that's the yearly rate, but the compounding is different. Find the balance 5 years, after 5 years when the interest is compounded quarterly. So these are all of our values that give us information. 5,000 is my starting value, so that's going to be my principal. 2.25, well, that's a percent. That's going to be my rate. 5 years, that's going to be how much time has passed. And compounded quarterly, that means that my compound rate, or how many compounds I have per year, is going to be 4. So I'm going to rewrite this problem. I don't know what y is. That's what I'm trying to figure out. And I shouldn't say y. I don't know what a is, capital A. That's my amount at the end. But I do know my principal. That's $5,000 times 100%. That's my start value, plus my 2.25% interest. That's equivalent 2.25% is equal to 0.0225. So that's going to be my rate. I just divided by 100 over the number of compounds. That's 4. Let's move over a little bit. To the 4 times the number of years, which is 5 years power. So this is my equation. This is pretty straightforward from here. I can simplify it as I go. A equals 5,000. 1 plus 0.0225 divided by 4. You can do that either on paper, in your head, or I'm just going to use a calculator. I'm going to divide that by 4. I'm going to add that to 1. So it's going to be 1.005625. I'll just put that number in there, 1.005625. And then 4 times 5 on the exponent is really going to be to the 20th power. Again, at this point, I'm just doing calculator work. I've already got that number in there, 1.005625. I'm going to take that to the 20th power, and that's going to give me a nasty looking decimal. I'm going to round to the nearest thousandth, so it's going to be 1.119. So I end up with A equals 5,000 times 1.119. I'm almost done. And actually, I don't even need to round that. I apologize. Let's not round that. Instead, we're using a calculator already. Let's save our rounding for the end. So scratch that. Have a little brain fart there. I've got this number. This is 1.005625 to the 20th power. Instead of rounding it now, let's just multiply it by 5,000. That gives me an exact value. And let's just round this to the nearest cent. $5,593.60. So my final value is going to be $5,593.60, because that 59 cents rounds up to 60 due to that tenth of a cent or hundred or thousandth of a dollar value. And that is it. So those are all the examples from this chapter, or additional examples to this chapter. I hope this was helpful. I think I went a little bit longer than I expected, but I feel like this might be helpful for people who are having trouble with the homework. All right, have a good day, everybody.